Well, this part of the tutorial is an overview or summary of a group of tutorials dealing with propagating electromagnetic waves. The remainder of the tutorials that form the set deal with the subject, the physics, in much greater detail, and then there are mathematical simulations to show the work explained mathematically, and then there are some worked examples, and then a number of practical applications, so you see how this subject applies to the real world. The course applies to and is designed for physics students taking the algebra-based course in physics, students taking the calculus-based course in physics. So now we'll go on and see the main points of where you can benefit and prepare yourself for the remainder of the tutorial. So there are 6 points. Let's have a look at them now. The objectives. The first one is to appreciate that electromagnetic waves have 2 components, and these satisfy what we'll see to be the wave equation, and this is an important part of describing what an electromagnetic wave is. And then number 2, to appreciate the very wide range of wavelengths or frequencies that are involved in the electromagnetic spectrum. And you will see that the visible part of the spectrum that we use to see with, of course, is a very small part, and the electromagnetic spectrum goes from wavelengths of kilometers or tens of kilometers, radio waves, right up to very short X-rays and much shorter gamma rays. Then the third thing is, how do we produce electromagnetic waves, and how do they behave when they're transmitted from one place to another? And that involves the attenuation due to distance and the absorption due to the material through which they're travelling. Well, here are the other 3 points, making 6 in all. Number 4 is the study of the wave equation that describes a propagating wave. And this involves 2 variables, both x and time. So it's a function of 2 variables, and quite difficult to understand the first time round. And then there are important parameters in this, wavelength, frequency, refractive index, and then finally the phase velocity. Indeed, the 5th point is the appreciation and calculation of the phase velocity, the speed at which a certain point on the wave will travel. And then finally, 6th point is, why should you know about it? Well, there are many applications, and we'll draw on and illustrate a few of these from communications, healthcare, and industrial applications. Well, this slide shows the actual wave equation. A is the amplitude of the wave, and then there are variables x for distance and t for time. But this wave equation describes all kinds of waves. Waves of an ocean surface, waves on a piano string, a violin string, sound waves. So it's not peculiar to electromagnetism. It's often derived from, say, applied to waves on a string. You would use Newton's laws of motion to describe the movement of the string when it's plucked, as in the violin string, and you arrive at this equation. So it's rather remarkable that the same equation appears out of the laws of electricity and magnetism. This is what it was Maxwell's great work. Now, looking at this equation, you see that A is the amplitude, say the height of water at a certain point, at a certain time, over the mean surface, or it could be the amplitude of the violin string. X is distance and T is time, and you notice it involves an important constant in there, v squared. V is the velocity of propagation. We'll arrive at this equation in a different tutorial, but we're going to use it now and see how it relates to electricity and magnetism and propagating electromagnetic waves. Well, now you see a solution to the wave equation. We haven't derived it, but I just wanted to acquaint you with what a solution looks like, a solution to that